Are you stuck on the 2021 AP Stats FRQ question number 4? Well, you've come to the right place, because in this video we're going to talk about exactly how to solve that problem from the 2021 exam. The question does deal with inference for a population proportion. It's a pretty good problem that goes through all of the steps. Let's dive right into it. The manager of a large company that sells pet supplies online wants to increase sales by encouraging repeat purchases. Okay. The manager believes that if past customers are offered a $10 off their next purchase, more than 40% of them will place an order. So if he gives older customers a coupon, essentially, to have some money off the next purchase, he believes that 40% of those customers will place an order, getting repeat business. To investigate the belief, 90 customers who placed an order in the past year are selected at random. Each of the selected customers is sent an email with a coupon of $10 off for the next purchase if the order is placed within 30 days. Of those who received a coupon, 38 place an order. All right, is there convincing evidence at the significance level of 0.05 that the manager's belief is correct? Complete the appropriate inference procedure to support your answer. Now, if you read this is not the AP Stats test, try to be mean or difficult, but they just give a lot of numbers. So let's focus on the important ones. First off, 40%. He believes that the true proportion of customers who are offered a $10 off coupon will actually place an order is 40%. That's what he believes it is. That's the key number. The $10 is not really needed. That's just the value of the coupon. It could have been $20 or 10% off or $40 off. They just chose $10. But that number is not actually going to be needed. Now, he is hoping that it's actually more. He is kind of hoping that the proportion is greater than 40%. He believes it's 40%, but he wants to increase his business. He wants to get a larger proportion of older customers to come back and buy more items. So that's what he's wanting. That's, because the question says, we want to test if his belief is correct. Well, this is his belief. He believes it's more than 40%. That's what we're actually going to test. Notice I'm not using p hats here. I'm using true proportions because that's what he's trying to get to, the truth. Now, the sample was for 90 customers. That was my sample size. And of those 90 customers, 38 out of the 90 did purchase an item using that coupon that they were sent. Now, this did come from a sample. So this proportion of 38 out of 90, and grab a calculator if you need to, that proportion is 0.42 repeating. So 0.4, 2, 2, 2, okay, a bunch more twos. But that is a p-hat. So here is essentially the question. Now, oh, by the way, this 30 days thing, I did another number you don't know. That 30 days is just there to try to trick you up, right? I hate that they do that. But that was just the time that you have to use the coupon. But to my statistical analysis, that doesn't mean anything. All right, so at the end of the day, it's actually quite simple. He is hoping that the true proportion is 40%. His sample was 42%. Now, let's be honest, 42% is more than 40%, but is it significantly more? Is 42% so much higher compared to 40% that we could officially claim that his belief is correct, that offering this coupon will get more than 40% of customers to buy something else, to place a new order? That's the crux of the problem. And that's what they want us to test. Now, we're going to do this with a significance test. That's the easiest and simplest way to determine if you have significant evidence of a belief, is with a significance test. Now, I believe there are 4 steps to a significance test. So before we actually dive into answering the question, I know I've been talking a little bit here, but I think it's important that you actually process the 4 steps to a significance test. Step 1 is give the hypotheses and name the parameters to be tested. What it is that you're talking about in the problem, like what is the proportion that you're dealing with, and what are your hypotheses about that proportion. Pretty easy step. Step 2 is to build the sampling distribution of the sample proportions based on the null hypothesis being true. So we're going to build a sampling distribution based on a population parameter that we believe to be true. And we do have to check our conditions to build that sampling distribution. Because let's just go back here for one more second. if I simply ask this question to my grandma's going to say, well, 42 is bigger than 40. Looks like we have evidence. But in the world of statistics, we know that things vary. So we need to build that sampling distribution to see, is 42% just a little bit bigger or is it a lot bigger? Step 3 is actually calculating the test statistic. That's going to be our z-score and the corresponding p-value. And then step 4 is actually making the appropriate conclusion to the question asked based on the p-value. All good conclusions are based on a p-value. Now, if you are following other books or other texts or the AP classroom information, they kind of combine steps 2 and 3 as one step. I like to keep them separate, but feel free. I mean, heck, you could put all this together and say it's all one step. But I like to have 4 distinct sections to my actual answer. All right, so let's dive right into it with step 1. First, we have to identify what it is we're talking about. Please copy the words from the problem. We're working with P, the proportion of all customers of the pet supply company who would place an order within 30 days after receiving an email with a coupon for $10 off the next purchase. I know that's a mouthful, but remember, proportions don't have a unit like inches or feet or millimeters. The unit on a proportion is just a bunch of words. It's what that proportion represents. And, you could just say the proportion of people that buy something, but that's too generic. It's the proportion of customers at a pet supply company who would place an order within 30 days of getting a coupon in their email for $10 off. I know it's a lot, but that's what we want to be here, super, super specific. All right, now the other thing we have to do here is actually name the test we're going to use. This is known as a one sample z-test because we only have one sample to help us make this decision. And we are using z-scores because in that normal distribution that our sampling distribution will represent, that we're going to base all of our information off of z-scores here. All right, now the other thing we need is our hypotheses. So our null hypothesis is that the 40% is true. It has not gone up like we were hoping the coupons would cause. An alternative hypothesis is that the true proportion of customers who are going to, place an order within 30 days, yada, 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 is actually more. This is his belief. The alternative is always the belief that you're hoping to achieve, and that's what the manager is hoping. So the null is always an equal sign. The alternative is always what you want. In this case, we want it to be greater than 40%. So there's a lot to step 1, but hopefully it's all not too bad, but you need it all there for step 1. All right, step 2 is actually, again, building the sampling distribution. So the sampling distribution for samples proportions of 90 customers who would place an order within 30 days is going to be described below. Now, again, we believe the truth to be 40%, but we all know that samples vary. So we say, all right, what would all possible p-hats look like? Well, the mean of all those p-hats should be, well, if the truth is 40%, the truth is going to be 40%. Now, again, samples are allowed to vary. So some samples might come back 41, 42, 45, 38, 39, 37%. But the mean of all of them is 40%. So make sure you understand our notation and our symbols there. Now, the standard deviation for all possible p-hats that we would see in a sampling distribution, pretty simple formula here, giant square root 0.40. The 1 minus 0.40 is 0.60. That would be the 60% of people who don't make a purchase, divided by our sample size here. So grab a calculator if you need to for that, but we should be getting 0.0516. Now that value represents the fact that, hey, samples are allowed to vary. They're allowed to be a little bit higher, maybe 45%, maybe 50%. They're allowed to be a little bit lower, 35%, 30%. All right, and then finally, the shape of this sampling distribution is going to be normal. That is not necessarily a given. We got to check our conditions here, but that is obviously a very important fact. Now, this last part here is all of our conditions. You can do this in bullet points, paragraph form, however you want to do it, but you got to do it. Now, the conditions for this distribution are met because A, the sample was random to avoid bias. Okay, that means our center is going to be unbiased and where we want it to be. 90 customers is probably less than 10% of all. It was a pretty big dog company, they said, or pet supply company. So you got to assume 90 customers is less than 10%, all of them, to assume independence. That means that everything's going to vary exactly as we calculated. And we're normal because our sample does contain 36 successes. So 40% of 90 would be 36 expected successes and 54 expected failures. Now, our actual sample had 38, I realize that, but we're basing this on the 40% that we believe to be true. So if it was 40%, we would expect to see 36 successes, 54 failures. To be normal for a proportion sampling distribution, we need both of those numbers to be 10 or larger, and they are. Now, the only way you don't have to waste the time with these conditions is if they give you a little teeny blurb that says, you are allowed to assume all conditions have been met. So, I mean, that does actually happen on the AP Stats test. Did not happen in this problem, but if that happens, you don't have to write all those conditions. It makes this particular step a lot easier. Now, it's not a requirement that you actually draw a picture of that sampling distribution. I personally like to. It's normal, so I made a normal model. In the middle is the 40% that we believe to be true. And then I went up 1, 2, 3 of those standard deviations. Remember, a standard deviation for this problem was 0.0516. And then I went down 1, 2, 3 standard deviations. Now, the reason why I like to draw the picture is this allows me to kind of get an idea of what might happen. Our sample, if you recall, was about 42%, which falls right around here somewhere. That instantly tells me, because I understand what I'm doing here, that that's not that high. That's not such a high number that I think that these coupons are doing a great job, and that should support my conclusion, but I need a p-value to make that conclusion. But the picture helps me see that 42% is not that high, and picture's worth 1,000 words. All right, so section 3 is actually calculating the test statistic, which is our z-score, and our p-value. Now, the only thing you need for this is your actual sample. You know, what was our sample that we're trying to use as evidence? It was 38 out of 90 or 0.4222. So my z-score is where that falls on the normal model. That's why it's called a z-test. So I'm going to take that 0.422 minus the center of the sampling distribution divided by the standard deviation of the sampling distribution, and I get a z-score of about 0.430. I am going to grab my calculator here just to show you that work. So 0.422. Now, actually, you know, this is not a huge deal, but I'm actually going to do the 38 divided by 90, getting me all the decimals. Subtract the 0.40, divide by the 0.0516. And I get that z-score of 0.43. Technically, if I do all that rounding, actually it should be 0.431. Now, that's kind of a minor thing. There's not going to be any major deduction of points for that, but just to be as exact as I can. Now, that actually confirms exactly where I put this. We're pretty close to it. This is +1. This is 0 in terms of z-scores. So 42% falls somewhere in between at a z-score of 0.431. That's not an unbelievably high z-score by any stretch of the imagination. Now, a p-value is the probability that of all possible p-hats, that one would be more extreme than mine. So that's more extreme, higher than 0.4222. Now, why did I not look lower? Because some problems look lower. Well, my sample was higher. So since my sample was higher than the 40%, and that's what the manager was hoping for, that it would be higher, we want to look greater than, because higher means more. And to do this, we're going to use our normal model. We're going to use a z-score greater than the 0.431. These are two equivalent statements, just one using p-hats and one using z's. But we're trying to find that p-value. Now, to actually find that, I'm going to go to my calculator here. I'm going to do a normal CDF. I'm going to go from 0.431, that's my z-score, to 99. 99 is acting like my infinity, essentially. And I get a p-value of 0.333. Now, let me graphically show you what that is. So here is my sample, and I'm finding the probability of all possible p-hats, that's what a sampling distribution shows, of all possible p-hats, the probability that a sample proportion of 90 random customers is more than mine, and we just found out that that's 33%. That tells me that my sample was not that weird. It was not significant. And that's what's going to lead me to my conclusion. So the first step of your conclusion is utilizing your p-value. Because my p-value of 0.333 is greater than the significance level of 0.05, I will fail to reject the null hypothesis. It did tell us to use a significance level of 5%. That means any probability below 5% would be considered significant and weird and rare. That would cause us to reject the null. But we are not even close to being less than 5%. So this is not weird. This sample is not that high. If you go all the way back to the beginning, I talked about the fact that the big question here was, is 42% just a little bit higher due to just variability, or is it a lot a bit higher due to the fact that these coupons are working and more than 40% of people are buying second items? Well, I just found out that 42% is just a little bit higher. My normal model shows me it's a little bit higher. My z-score shows me it's just a little bit higher, and my p-value shows me that if 40% is the true proportion, then seeing 42% or higher is actually quite likely. My sample is not weird. So there is not convincing statistical evidence that more than 40% of all customers of the pet supply company would place an order within 30 days after receiving an email with a coupon for $10 off the next purchase. I know that that's a mouthful. Most kids are going to try to cut corners. They'll just say, there's no evidence that 40% is wrong. But you got to give the context. There's no evidence. And again, what was the manager looking for? That more than 40% of his customers who get a coupon within 30 days will use that coupon that's $10 off to buy a new item. Well, that's what he was hoping. His samples showed more than 40%. But sorry, it just wasn't significant enough for me to officially say that I know for a fact it's more than 40%. Now listen, at the end of the day, it might be more than 40%, but my sample's not a significant one enough for me to make that final claim. All right, there is a part B to this. This is kind of a long problem. Based on your conclusion from part A, okay, we failed to reject the null, which of the two errors, type 1 or type 2, could have been made? And then interpret the consequence of this error. So first we got to remember what the type 1 and type 2 error is. So to do this, I think about my null was 0.40 and my alternative was that it was more than 0.40. So a type 1 error is when the null is true. It is 40%, but we reject it and think it's higher. Well, that's not what we did. We did a type 2 error, or potential for a type 2 error. A type 2 error is when the alternative is true. It is more than 40%, but we failed to see that. And when my conclusion was that I failed to reject the null, I am at risk for a type 2 error because I'm confident in my decision. I didn't do any of my work wrong, but when I say that, listen, I don't think it's more than 40%, there is a chance that I'm wrong, and maybe it is more than 40%. And that's what a type 2 error is. The truth is the proportion is more than 40%, but we failed to see that. So anytime you fail to reject a null, you are at risk for a type 2 error. So in this case, a type 2 error is made by failing to reject the null hypothesis that 40% or less of all customers of the pet supply company would place an order within 30 days after receiving an email with a coupon for $10 off the next purchase, when in fact it is more than 40%. So they wanted you to explain that we could be having a type 2 error here, not type 1. Type 1 occurs when you reject the null. Again, possibility of a type 1 occurs when you reject a null. And so I have to just explain that in context. And then now here comes the consequence. What if it was more than 40%? That means the manager did have a cool program giving these coupons through email that would increase sales. But we claimed that that wasn't the case and that it was still 40%. So the consequence here is the manager may decide to not use the coupon promotion when it actually works. Now, at the end of the day, there's no way of knowing if I made this error or not. That's not the point of the question. It's just the possibility. Anytime you make a conclusion, there's always a chance that you're wrong. We don't want to be wrong. We hope we're not wrong, but there's always the possibility of it. Not that our work is wrong, that just, you know what, our sample was a weird one that didn't show us what we wanted. So when you fail to reject the null and say that we don't have enough evidence to go with the alternative, there is a chance you make a type 2 error, meaning that, no, you should have rejected the null and you should have gone with the alternative, but we didn't. So if the truth is that the program works, we did not see that, hence the manager decided not to use the promotion when it actually does work. The most challenging part of this problem is the fact that when you write the unit, it's long-winded. It's the customers that are going to, from a pet supply company that would place an order within 30 days after receiving an email with a coupon for $10 off the next purchase. Nobody wants to write that, but listen, you got to do it because you always want your answer to be well-written and in context. All right, a little bit of a longer video here, but hopefully you liked it, hopefully you enjoyed it. And these types of significance tests are all over the AP test every single year. They're never left off, let's put it that way. So hopefully this problem makes sense and you understand the proper wording of the conclusions and the interpretations.